welcome to the second of our post-lunch talks. Adnan Shahzada and Fabio Badali from Cleo, fintech company, are going to be talking about enriching transactions with the Cleo MLOps framework. Adnan did his PhD at the Polytechnic University of Milan in computer science. He's passionate about building self-serving, self-adapted intelligent software systems, and he's got more than 12 years of experience both in academia and industry. And he's been a senior data scientist at Cleo for the past 3.5 years, working on various machine learning models powering the Cleo app. Fabio's a software engineer with experience in ML and big data domains, with a particular interest in DevOps. He's worked on several layers of the technical stack, with a particular interest in the infrastructure layer. And as a data scientist at Cleo, he's working on MLOps and data solutions. Over to you.
Well, thank you all. So today we are here to tell you about how we do transaction data enrichments at Cleo with the Cleo MLOps framework. So to start with, I'll tell you a little about who Cleo is and what kind of data Cleo has and why it needs to enrich the transactions, how we are actually using machine learning services, building machine learning services for that, and a framework that could actually support deployment and serving those ML services for transaction enrichment. So to start with, who is Cleo? Cleo is an app, we call it like a relationship that supercharges your financial health. It turns the complexity of your financial life into a conversation, the same kind of conversation you could have with a friend. And interestingly, improving the health, it's like $65 million plus have been saved for US users in terms of overdraft fees. And also 84% of the users feel better about their money after using Cleo for more than a month. How do we achieve these systems is, because at the core of the Cleo, one of the pillars is how we can help users spend better by providing them personalized insights, recommendations, and goal tracking over the period of time. We can show them when users have their Bank Connects account with the Cleo, they can say how their balance is trending over the period of time, what are the spending breakdowns, and they can see where they have been spending their money with. And with the personal insights, they can actually help track to spend better over the period of time. The other important pillar for Cleo is how Cleo can help with reducing the different fee structure that's in the US, like the legacy bank system, and how we can reduce especially the overdraft fee. So Cleo provides their users with some of the overdraft fee that could help them avoid overdraft fee and also improve their credit score over the period of time. On top of that, it provides users with an engaging experience, which is quite different than the other banks that usually work with. So it has a popular feature like Roast Me, where they can actually have their spending breakdown sent to them in a roasting manner, which is quite a popular feature. Similarly, there's a feature called Spender, which is also something that they can mark their spendings as whether they regret it or whether that particular spending was necessary. So this is something that's actually helps them engage with the app and also try to see the insights where it can help them spend better and avoid fee that can help make their health better. So it all sounds good, but the question is how we can enable all this through Cleo. At the start, users, when they connect their bank accounts with Cleo, we can see these raw transactions coming in, which is quite unstructured, and most of the times you don't actually understand what this means if it's presented to user in this way. So the first task would be to make sense of this data in order to make user understand what they've been spending on, how their finances looking like, and providing them insights. So this is where this transaction enrichment comes in. We get this raw data. We need to enrich those transactions with the right level of information, extract useful entities that can be actually used then to provide useful insight back to the user. So it's like curating, pre-processing, and contextualizing the user bank transactions in order to like find them the right advice where they need it. So transaction data is complex. So when we have these raw transactions, as you see in some of the example as well, it could have multiple entities like merchants, point of sale terminals, information, transaction types, banks, and different payment and card processes. They could be present in the transaction description in different orders. So there's a bit of variability in terms of how they appear in the raw transactions. And also, even the same merchant and similar transaction with different banks could actually appear in a very different structure. So challenge is actually to extract and provide users like with this clear brand names, categories, some patterns from those transactions, the recurring themes. But in order to do that, we need to actually process them and make sense of all the transaction data that's coming in. So to summarize, transaction enrichment is something that sits at the heart of the Cleo. So whenever a user connects their bank account, this Cleo's engine actually enriches their transactions and tries to extract useful entities like merchants, categories, recurring incomes. And based on these entities, we can actually provide them with the useful information that's actually based on those extracted entities. So we have a large amount of data, so we could build some interesting models based on the transaction data we have and can generalize things from different banks and situations. So around 35 million transactions per week is actually we get in Cleo for the users. For this particular task, as transaction enrichment has different components as we have seen. So in this particular talk, we will be mostly focusing on the merchant association, which is just one component of the whole transaction enrichment process. Why we choose to have this topic is it's a huge downstream impact, and it's like the first thing in the pipeline of getting that data enriched as well. So we have merchants. In merchants like Amazon, Deliveroo, Thames Water, but then there could be categories which is can actually use the merchants data as well. For example, Amazon could be shopping, Deliveroo could be eating out. This could be actually customized to the user as well, but for example. And then also like for finding the recurring patterns from those transactions. For example, some dollars paid to Thames Water on the last day of every month. You need to actually have that merchant there in order to find that recurring patterns among the different transactions. So how merchant association happens at Cleo. So historically, we were having some strings and regex matching, so regular expressions. There were lots of regular expressions written at the back end, which were like optimized for latency. And the idea was like for different banks, we could eyeball the data, which transactions coming in, how we can extract the merchants, write hand-coded rules for that, and then do this for every bank or user we see that's coming in. But obviously, this approach lacks flexibility, and because you can fix the hard code rules, but then there's slight variance or a new bank could actually disrupt that. This could end up in lots of duplication where we could have a similar merchant, but they would eventually have to be matched with the right merchant that we already existing in the database. Similarly, maintainability and scalability is an issue because the user base is always growing. They would be having different banks all the time. So having all those regex writing for all the banks that we have, all the users we have, would not be feasible. So this is what it looked like previously. We have lots of logic at the back end, which actually checks what are the transactions, what are the descriptions, how we can match it with the existing merchants that we have, or some of the patterns that we can deduce. But it's even before that, we have to do some cleaning as well to make those relevant strings out of that. So as you can see that regex and syntactic matching is rigid, and it's very hard to find like the cater the situations where the unanticipated variations occurs. Similarly, bank dependency, as I talked about, duplicated merchants, and also it's very hard to get this system a comprehensive one because it won't end. It would always need to be evolving over the period of time. So what do we want to do then? So what we wanted is take all this backend logic that we have in terms of like the training, regexes, and pattern matching, and take a transaction description, feed it into a machine learning model that can actually provide us with a merchant. So in this way, where there won't be any pre-processing or cleaning would be required. No regex maintenance would be required. There's like, it would be a better generalizable mechanism as compared to the old system where we have the regexes, and an easier incremental development would be supported by this, because instead of like eyeballing where we are not trying that, we can fit in more data, do some annotations, and add it to the training set and make it evolve over the period of time. So the first thing we thought about, as was discussed slightly in the previous talk as well, to use this named entity recognition system, because it's like we have a raw text, and then it can have different entities in it. For example, in our case, merchant categories could be some entry. In the example, you can see that Amazon could be a merchant, which is a company name, and a purchase could be a transaction type. So we already have some data available where we, through our regex matching, we have the raw transactions and then the associated merchants for that we can use to label and tag those transaction description log. For example, if this transaction description was already processed by the existing system and we have Amazon as a merchant for that, we can see where Amazon happens in this token and label it as a merchant entity and train our system on top of that. But the problem here was it was a bit tricky because there's lots of variability how this merchant appears. Like this could be abbreviated by AMZN only, and then to find it back and label the data was quite difficult for us. Also, if we train such a system, it would eventually app up because it would be tagging each token as whether it's this particular entity or not. It would end up in having lots of duplicate merchants again, which is our initial problem. So the next thought was, rather than having it a named entity recognition problem or a tagging problem, can we modify it as a classification problem and have each merchant as one class? But the issue there was like there's around 8.7 million merchants in our DB, which are too many classes for a classifier. But if we further drill it down, it seems like there's a long tail of merchants which are not very frequent. And if we only consider the top 5K frequent merchants, it almost covered 86% of the transactions that we already have a merchant for. And if we bump it to like top 40K merchants, it covers around 92% of the existing transaction coverage. So there's opportunity here that we could actually build a top K merchant classifier rather than a holistic merchant classifier. So for this purpose, we've been using FastText for already, like in one of our previous tasks, we discussed how we have implemented in our NLP chat intent classifier. So this is something that we already have a trained embeddings. By the way, we need to have a custom embeddings trained for this because the raw transaction description data is pretty niche, and normally the pre-trained embeddings that's trained on like English language, it's not as ideal as we could do with the custom training. So idea was to use FastText classifier, which is like a different than the tagger. So we won't have that labeling issue because we have one-to-one mapping. And also like we will have a consistent output. So whenever a certain merchant would match, it will always come up with a class rather than tagging each individual token and having a different duplications of the same entity. So how we formulated as ML problem. So we took like top 40K frequent merchants that happened in January, and took the transaction associated with those merchants. We had to undersample it a bit because there are many merchants which have lots and lots of transactions, which are like very, very frequent ones, where there are many which have only few of them. So we filter it to not have more than 10K samples for each given merchant. For the labeling, we bootstrap it with the existing merchant data that we have, but with some cleaning that's done on that. So one thing we also did is like we grouped together similar descriptions and then see what's the top merchant in our DB to label that so that we can reduce some sort of deduplication. But even that, the deduplication problem was severe. Like this is just example of one merchant, which lots of merchants compared to which would be actually one merchant in the DB. And you can see that there's a lots of variation of the similar merchant based on there's some additional information or lack of some information or missing information. So we needed a fix to actually solve these kind of problems. But if you look at this in detail, it looks like we can just write a few more rules to actually get rid of this and associate this with a single one. But if we had to do this for all the merchants, it would then not scale up again. So we needed a mechanism that can generalize and scale and give us some of the potential duplicates that we have in our label set. So we could have a better labeling and hence a better merchant classifier with less duplicate merchants in it. So for this purpose, we employed entity embed library, which actually is an implementation of an Amazon approach. So what it does, it's a multi-attribute matching algorithm. So you could have different attributes for a particular entity. Like for merchant, you could have name, maybe an average amount. And then for each attribute, you have token level embeddings, which are actually then combined together to form attribute level embedding, and then they are concatenated together to form a tuple or row based on a particular merchant. So it then uses contrastive training to build the embedding space. So contrastive training is something where similar merchant vectors would be similar together in the embedding space, whereas the different ones, so for each iteration, it takes like, okay, this is the sample that it's currently processing. It would take other sample from a similar class, put it on a similar class and make them together, the matrix more closer in the space, whereas for the different class, it could also sample one and then also try to make those vectors far away from each other. And in this way, it can build a embedding space that could actually help us embed all the different merchants that we have in the embedding space, and then could be used for clustering then later. So we could define a threshold that if similarity between two clusters in this embedding space is greater than that, we can mark them as duplicates. So this is something that we use for the duplication of the merchants. So we applied this on the labels and reduced the number of labels by eliminating some of the duplicate merchants and merging them together, and retrained the classifier on the deduplicated labels. So how this all fit in? So we already had an existing system, which was mostly based on pattern matching. And then we are building this merchant classifier, which actually targets to handle the top K merchants. So because it's not a holistic system, because it would only take the top K merchants, we still need to fall back on the existing system when the coverage is not there. So in our initial understanding, we thought that it should cover at least 92% of the transaction that we already have merchant for. So a transaction is fed into a merchant classifier when we receive it, and it gives back a merchant name with a confidence score. So if confidence score is greater than some threshold that can be determined by the training AUC and a validation AUC, or we also kind of learn it online after a few iterations, then we can assign the merchant to it. If not, we can fall back to the existing system of regexes and pattern matching to assign or allocate the merchant for the long tail end of the merchant database that we have. So in this way, we could have this new system that's kind of addressing most of the issues and targeting the most of the transactions that we cover. And then there's a fallback thing that we do to address the latent. So what we have done till now is like, we had the transaction enrichment problem. Merchant classifier was one of them. We built one service that is a machine learning that would actually migrate the existing system to something that's a machine learning system. And we have deployed a model and tested it on the manually ran some samples on that. But this is still not productionizable model. So we were testing it after training a model. We are now testing it on the offline data because we already have the data from the existing system where we had lots of transactions which have the associated merchants for over the last few weeks. So we took this data, also ran it manually through this newly built model and tried to compare their results. So what we were looking at is merchant classifier coverage on all the transactions, match rate and effect on overall coverage, and the new merchant creation rate. So this is also important because when we try to match a potential merchant from a description to an already existing merchant, if we don't find one, we tend to create or consider it as a new merchant. So if there's less duplication in the DB, this merchant creation rate would also need to go down because we'll be matching more merchants and creating less new merchants. So these offline testing results on the few weeks of data, so it tells us like we got 91% coverage of the transaction through classifier, where the current system has an associated merchant, which was kind of almost on par with the expected, which was like 92%. Plus, we also have 9% additional transaction coverage when classifier was used with the existing merchant association system as a fallback. So this was a good gain because in the classifier, it was able to actually handle some of the merchant from the transaction that have not associated a merchant with the existing system. So it actually get them right through some of the pattern matching that was not possible with the regexes. So it has some additional gain, but at the same time, it has missed some of them because it was not as confident as we had with the merchant classifier. But the overall gain was like the 9% additional transaction coverage. And in the last few weeks, there was like 13% less new merchants that was created every week as well, which is also a quite good result. So what was the next step? So before moving to that, if we want to migrate this service as a machine learning service, also iterate it over it and replace our existing system, there are some constraints and concerns that we need to see. So first one is the batch handling. So it should support for the batch job or request, because if we have to call this service from the backend all the time, we can't do this on transaction-wise, so it should be a batch of transactions. Also, the backend rules were quite optimized for latency, and it also required to have that level of performance in terms of what we currently have. So it should be as efficient as that. And the last important bit is online testing. So we want to gradually test this on certain users without like promoting this straight away to all the users that we currently have. So we need a mechanism to do this online testing to evaluate and flag any expected behavior. It's also important to like split these users, but also probably have this accommodation to have different endpoints at the same time with different testing that's going on. So we have multiple endpoints that we are comparing each other against. So we need that factor as well. So then the question was how we can efficiently deploy, serve, and test our machine learning model that actually not only this merchant classifier, but in the future as well, that would actually provide us the tools to migrate all our backend logic in terms of machine learning services, do this efficient iteration over them, and also help the machine learning engineers to iterate quickly over them. So I guess now Fabio will let you know about the rest.
Yeah. Fabio here, data engineer at Clio. So the framework, we are still looking for a name for the thing that we built. Basically, we are in this squad, Mike squad, that is building the infrastructure for the pillars that Adnan mentioned before. Okay, so quick recap of the why. So we said that we have serving, deployment, and monitoring. We want to have those three things. But what we had before the framework? Before the framework, we had different solutions for different services regarding serving. We were using SageMaker for deployment, but without a standard way to build our images. And we had almost no monitoring. So what is the framework about? Again, deployment, serving, monitoring. We want to find an easy way to deploy our services. We want to find an easy way to serve our models. Also, we want to find an easy way to profile, trace, and monitor our services. Yeah, you guys right. Everything is about easiness here. This is also because we are a platform team, so we want to be as much invisible as possible to our data science team. We want to provide a way for them to work in an easy way, and we don't want to be part of the process too much. Yeah, we are basically switching our mindset, our paradigm, from having machine learning models to have machine learning services. These are metrics coming from the OKR of the Mac squad, of the infrastructure squad. As you can notice, actually our metrics are more about the easiness of what we built. We saw that our data science team spent just 2 days to build the merchant classifier that was mentioned and described before by Adnan. And we spent just 10 minutes in order to profile the code of another service in order to improve by 50 times the performances of that service. That is another important metric. We are proud of it, but it is not our core metrics. Our core metrics are more about the usability of what we built. Okay, so into the 3 pillars that I mentioned before: deployment, serving, monitoring. Deployment at first. This is the general architectural diagram of the deployment solution that we have right now. As you can see, all our code is inside GitHub. Basically, every time you are pushing something, you are triggering a Circle CI pipeline here. The Circle CI pipeline is taking care of a couple of things, among which testing, integration testing, and the integration testing is done both on Docker and SageMaker. That is our hosting solution. We are using S2I build in order to build our Docker images. S2I is a tool that is enabling the possibility to inject some source code inside a builder image and to build another image. That is the one that we are using during serving. We have AWS as a hosting solution, as I mentioned before, and we're using Terraform in order to deploy the resources, both on AWS, that is our cloud provider, but also on New Relic and Rollbar, that are our monitoring tools of reference. Online testing. We mentioned before that we want to be able to have different versions of the same model in production at the same time. We enable the possibility using a GitOps approach. This GitOps approach is basically you can create a new pull request in which you have the version of the code that you want to deploy in a segregated environment, and you can just label with deploy the PR, and you will be able to trigger the creation of this segregated environment. This is very useful. You can manage the whole life cycle of the segregated environment, but this is very useful, especially when we do some A/B testing, because the user can be routed to the master service or to the pull request one, accordingly to some logic, some bucketing that is defined. The split is defined in an admin panel that we have on the Clio app. Everything is integrated with Slack, so every time you are trying to deploy a new service or a new version of the service, you will receive this message in a channel that is saying awaiting for approval. You can approve, and hopefully you will receive this deployment succeeded message. Into the serving. So this is a general description of the service solution that we have right now. As I mentioned before, we have SageMaker endpoint that is like our deployment unit. Then inside each SageMaker endpoint, we can have different SageMaker instances accordingly to an auto-scaling policy that we defined, so accordingly to the load that we are receiving in the service at the time. And inside each SageMaker instance, we have a container that is defined with a Docker file. That is the one built by STUI, the one that I mentioned before. And inside the container, we have gunicorn, then a lot of unicorn workers accordingly to the size of the instance, and then fast API application, that is this thing here. This thing here is made by framework server code, that is some generic code that we coded and maintained in another repo, and then by ML service code, that is actually the core logic that is implemented by the data science team. So we can say that this is a thing that just works for data science team. They don't have to care about Dockerfile. They don't have to care about building stuff. They just have to be sure that they will be able to focus on things that matters, like the core logic. But what is this service ML code that I mentioned before? Basically, it is this, which is a JSON schema. You can define the input and the output of the service using a JSON schema. This is already connected to OpenAPI because we are creating an OpenAPI spec that is used in order to improve the communication between the engineering and the data science team. And it's also connected to the generation, some code generation that is creating Pythonic models that are used for automatic validation. So data scientist doesn't have to care about, I have this transaction ID that is an integer, I have to be sure that I've received an integer. No, this is something that happens in an automatic way. You just have to define the JSON schema. Of course, the service code is not just this, but it is also the implementation of the model. So we have a class. You have to define a method in order to be able to initialize the model. This is a very complex thing. Then we have predict and batch predict, basically. Batch predict, that means that we are fulfilling the other requirements. We are able to handle batches. This depends on the content type of the request that we are sending to the service. If it is a JSON, you will be using the predict. Otherwise, you will be using the batch predict if it is a JSON lines. You can configure way more things, Docker labels, a lot of other stuff. For this reason, we have created a CLI, and there is this command, Cleo MLOps create. It is creating just a skeleton project with all the files that you need and that you can configure, and you just have to do whatever you want with the files that we have. This is a very interesting feature that we have. This is a new one. It is called server-side batching. So basically, this is the common situation before the adoption of the server-side batching. There is a client that can do both single request and batch request to the ML service. As you can see, the two paths are completely separated. I mean, single predictions are routed to predict, single responses go to the client. The same is also true for the batches, but with batch predict. So server-side batching is basically introducing a new module in the middle that is able to create batches out of single requests. So we are taking single requests, we are batching the single requests inside batches, we are using batch predict, we are unbatching the response, the batch response, and we are providing the single responses to the client. This is a good way to optimize, on average, the performances of our services. On average, of course. In fact, we had an average speed up on the anti-fraud endpoint because we have more than just the transaction enrichment services in production right now. We were able to optimize also the anti-fraud endpoint using server-side batching. Into the last section, monitoring. Okay, so monitoring for us, it's all about quality. Again, we want to have a service. We don't want to have a model. We want to have something that is reliable. It is in production. We are able to ensure the quality of what we are doing. We can debug it. We can audit. And for doing this, our service is integrated with a couple of partners a couple of monitoring tools that we're using, like New Relic, in which we are storing the metrics, Rollbar, in which we are storing the errors, logs are stored in CloudWatch, in our case, because we are on SageMaker. Cleo Data Capture is another tool that I'm going to describe in a couple of slides. But before, metrics again. This is a New Relic dashboard, and this is created with Terraform in an automatic way. So we are creating all the infrastructure that we need, also for monitoring, in an automatic way with Terraform. I can tell you that this is actually the dashboard for the merchant classifier. So what Adnan said before is what we did with this dashboard, for instance, and a couple of other dashboards like this. We ensured that the quality of the classifier, the performances of the classifier were good, thanks to this thing. They are actually good, as you can see. Of course, this is something that is updated continuously, so we are also able to ensure that the quality is always good, not just once. We have tracing. We are using distributed tracing with New Relic, so you are able to see all the traces of your requests to, for instance, external services or data sources, if we have any in that classifier, in that service. We are using tracing IDs. We have 3 of them. The very first 2 are very, very, very technical. They are used just to distinguish between different requests and responses. The last one is the user ID. The user ID is used in order to, all of them are, by the way, are connected directly, are also stored in the monitoring tools that we have. So using the last one, you can see, for instance, that which are the people that are impacted by an errors, for instance, in Rollbar. And for us, it's very important. We have alerts on Slack for both New Relic and Rollbar. As you can see, this is for merchant classifier. Okay. Last thing, data capture. So data capture is basically a way that we are using in order to capture and store all the requests and responses that we have in our services. This data is correlated with service metadata, like Python libraries, Docker tag, whatever, and custom metadata. So from the core logic, you can decide you want to push something more in the data capture record, something more like the features that you're using. You can log the features that you're using. Everything is stored in S3 using Parquet in a partitioned way, so it is very, very fast to access. And it is exposed as an external table in Redshift Spectrum here. So you can just type this on Redshift, and you will be able to see the data of the data capture. It is an asynchronous capture, so it is not impacting at all the performances of the service. Quick slide into the future. So we are doing more and more things. In this very moment, we are exploring streaming feature engineering. We will do experiment management. We will handle also model training. We are evaluating to adopt Kubernetes and to migrate out our current hosting solution, and more. I don't know if I have, yeah? Okay, so this is feature engineering, what we are doing right now. As you can see, this is a slide, a very abstract slide that is describing what we want to do. As always, we want to make our data scientists happy somehow. As you can see, we want to find a way to define in a single way the features and to have those features available immediately, both for training and serving. I can replace these abstract things with components that we're using right now. I don't know if someone can recognize this. This is Flink, Apache Flink. This is Debezium, because we have data in the operational database that we're using on the app that we would like to use in order to compute the feature. So it is a CDC technology. We can capture all the changes in the database, and we can adapt the features accordingly to this. We are evaluating to adopt also domain events in Kafka. And we are evaluating right now the usage of Fist as an interface. So we will have both online and offline store for the features, and we will use Fist in order to access them. We are writing, by the way. It was like, okay, cool. Any questions?
Thanks, Adnan and Fabio, for a really interesting talk. We've got time for about 3 minutes of questions.
Regarding the deduplication method, right? assume it's not determinate algorithm, right? Every time you rerun your deduplication, you will give out a different output, right? If you don't set the states, assume.
Yeah, so you're asking about the deduplication?
Yeah.
And yeah, the question is like this deduplication is not part of the algorithm of like the merchant classification, and you have to rerun every time the duplication before retraining.
No, what I'm asking is, you have, can you go back to the slides?
Yeah, sure.
Sure. Almost there.
Okay, so go back one more. Where you have the tables already.
Okay.
Yep.
So every time you run this algorithm, do you know in advance which this row will become its label after deduplication? Assume you don't know, right?
Okay, that's a great question. So the question is like we have lots of duplicate merchants here, and the deduplication algorithm that we discussed would get you like cluster them together, but how you can actually resolve them back to like one merchant name, because there are so many, we can say that okay they duplicate, but what's the right one? So there's two things that we do currently. So we have an external company database name. So we try to see like which one of them actually matches this particular one in the external DB. And secondly, if this merchant has been there, some merchant which has been there for long, and we have like a very, very high volume of transactions to that merchant versus some of the other merchants that's matched, which has a significantly lower one. So we can use also that information to actually resolve to that highly frequent match.
Thank you.
Did I hear correctly that you train your own embeddings for the transactions? You could have used pre-trained embeddings, but it didn't work.
Yes, so that's right. So we train the custom embeddings, not use a pre-trained one. Yeah.
What method did you use for that?
So there's two ways. So we have embeddings both in like what we use in the deduplication work and a merchant classifier. So the fast text actually it uses fast text embedding, but we learn those embedding in a supervised way by providing them the training labels. So that's the one. And for this particular one, we actually trained unsupervised fast text embeddings to feed this into and encode that system into that.
Hi, I was wondering if you could tell us more about the work you want to do with the feature store piece, how you actually want to use it.
Yeah. Let me take the slide back. I'm fast. Okay. Yeah, we would like to use Flink in order to compute in a streaming way the features. So every time something changes, Flink will update, having a very, very heavy state. It will update the feature. And basically, we implemented here a thing, a couple of things, actually. UDF that is used in order to encode in protobuf the features that we're computing here for being retrievable by Feast. Because Feast on online store, for instance, on Postgres, we are trying with Postgres right now. On Postgres, it is using protobuf in order to store both the value and the entity key. So we have created a Scala user-defined function here that we are using in order to store the protobufs. We would like to use then Feast with online store Postgres and offline store something on S3. We didn't decide yet. The idea is to use probably Delta Lake.
So I think we need to end the questions there. So thanks again to Adnan and Fabio.